In this video lesson, we're going to learn how to find the area between curves, and we're going to do this by using integrals. We're going to start off with the situation where we explore a graph of f that's always above the graph of g. So let me just draw some arbitrary f of x. So here's f of x up here, and it is always above g of x, which perhaps is down here. And it doesn't really matter what they look like as long as f is always above g. And we're told that the area in between them, so that's going to be this area right in here between them, is equal to the integral of f of x minus g of x times dx. If we think back to all those rectangles we were drawing in our Riemann sums, we can take a single rectangle and take a look and see how this width we would call dx, so that's that part of the integral, and the height of the integral is the top function minus the bottom function, f of x minus dx. And so that's how we get this portion. This is the height of our rectangle, and this over here is the width of our rectangle. And we're adding up an infinite number of rectangles all the way from here, which we're going to call A, out to here, which we'll call B. All right, so we're going to get another visual on this. In this case, g is less than f of x just in this portion. And so if I take this graph, I could think of this whole region like this and shade it in red. I'm going to just give a pictorial view. So I can take that region, and that red region is equivalent to the integral from 0 to a, for a to b rather, and that was this top function, which was f of x. So that's f of x dx minus, and then I could find the region below f of x like this. And if I subtract that portion, you can see what's going to be left behind. So I'm doing a little minus sign here. And that portion was the integral from a to b of g of x dx. And when I subtract those, what I get is this top portion here. You can see if I put that in there, it would make this if I could draw well. And so that then equals this over here, which is the integral from a to b. And we can combine this subtraction. There are two separate integrals here, but over here we can combine them to be f of x minus g of x all times dx. All right, so let's try this with an actual problem. Here we have these two parabolas. You'll notice the first one leads with a negative x squared and the second one with x squared. So if I want to label my graph, the one that opens down is f. So this is this one. And the one that opens up is g. That's going to be this one. And so I know my integral is going to be the integral, my top function is f of x minus g of x. And of course, the width of every rectangle is dx. The problem is it's not obvious. Where do I start? This is my A, and where do I end? This is my B. Now, while we could do this one algebraically, we're going to do it on our calculator. I've already got the two functions sitting in here, m I y equals. And so I'm going to go ahead and hit graph. And I can then go to second, trace, and I have this option intersect. So I'm going to go to 5, and I'm going to just get near one of them. So I'm going to press enter 1, 2, 3 times. And that's at 1, 2. So let's come over here. I'm going to just label this point. This point is 1, 2. And then I need to get the other point. So I'm going to hit second, trace, intersect again. And I'm going to arrow over till I'm closer to this one and press enter 1, 2, 3 times. And there it is. It is at 3, 2. Oops. Get my pen to work. There we go. Oops. And there we go. 3, 2. Okay, so now when I'm doing the limits, I want you to notice that a and b are x values. So I'm going to actually go from 1 to 3. And now to get my final answer, I can go back into my calculator. So here it is. And I'm going to do second quit. So math. And I'm on the old version here, so we're going to see fn int, and we're going to do, let's see, my first function, let's see, was my, yep, so that's my f of x. So vars yvars function y1. That is not where I wanted it. Let's try that again, hit delete. And I should have a negative in there, so let's fix that. Oops, I can't see. Here we go. Okay, so second quit. Okay, so vars yvars function y1 minus vars yvars function y2 comma x comma 1 comma 3, and we'll have our answer, which is 2.667 if we go to 3 places. All right, so 2.667. All right, let's try another one. So in this case, here's a parent function. I know what it looks like. I want the area of the region under e to the x. Now I should remember that e to the x goes through 1 right here. And above y equals 1, so here's y equals 1. And I'm doing it between 0 and 2. So here's the area I'm looking for. So I can do the integral from 0 to 2 e to the x minus 1 dx. So top function e to the x, bottom function 1 from 0 to 2, and now all I need is a calculator to get that final answer. So math 9 second. Let's see, we've got e to the x minus 1 comma x comma 0 comma 2, close our parenthesis, and there it is. Go to, oops, let's see what went wrong. Oh, too many commas. There we go. And 4.389. Okay, so we've got that answer. All right, let's take a look at what comes next. This time we want the area between sine x and cosine x between 0 and pi over 4. And again, it really helps to draw the picture. So I know that sine x kind of goes like this, and cosine x goes like this, and I know they're equal to each other at pi over 4. So here's my picture, and remember cosine was on top and sine was the function below. So I've simply got the integral from 0 to pi over 4 of cosine x minus sine x dx. And I'm throwing that in the calculator to get an answer to you. And we're going to just take a look at our next one. And this one I've got the graph already drawn for us. We're looking for the area between sine x and cosine x all the way from 0 to 5 pi over 4. Now let's just review our unit circle for a second and remember that sine x equals cosine x here at pi over 4, and it also, they're equal here at 5 pi over 4 because our x and y values are the same. So here they're both root 2 over 2, and over here remember they're both negative root 2 over 2. So that's when they're equal, and that shows up like this on this graph. So here is pi over 4 when they're equal, and over here's the other time when they're equal at 5 pi over 4. Now what's interesting here is to watch that they switch places. So sine is this red part of the graph, and it's the function below and then above, and cosine, we'll make that one green, is up here. It's above at first and then below. So in order to get this problem right, we actually need to write two integrals. Our first integral is from 0 to pi over 4, and for this one, cosine is on top. So cosine x minus sine x dx. And of course you could take your answer from the last part for that. For the next part of the integral, we're going from pi over 4 to 5 pi over 4, and this time the function on top is sine x. So we're going to have sine x minus cosine x dx. All right, Again, you can throw that in your own calculator to get an answer. And we're going to lastly do some comparing of integrals, and this is going to help us estimate answers. So we're going to take a look here. If f of x is less than g of x, then we know that the integral from a to b of f of x dx has to be less than the integral from a to b of g of x dx. All right, that one's kind of obvious. Now let's go to this one. Now here what we have is a big M, kind of big M is for the maximum value on f, and we have little m, which is the minimum value on f. And we have this function. I'm just going to trace out the actual area here, like this, oops, like that. So that actual area is this integral right, we'll try and get the whole thing, there we go. Right there. So that's that area. Now what we have also is we know it's less than if I took this entire blue box here. I know that that red region is less than that. And apparently the whole thing doesn't want to drag with me. We'll bring the top, there we go. So we know that that red region is less than that. Well, what is the area of that blue region? That blue region has a height of m and a width of b minus a. We also know that it's bigger than this rectangle. And that green rectangle has a height of little m and a width of b minus a. So let's see how this plays out in an actual problem. So here we go. We're going to explain why the integral from 0 to pi over 2 of sine x dx is less than pi over 2. So let's take our sine x, and we're going to sine x goes like this from pi over 0 to pi over 2. And so here is the actual area of sine x. But we know it's going to be less than this rectangle right here. Oops, which I'm having a hard time drawing on this. Okay, there we go. Now that blue rectangle has a height of the highest point sine gets, which is 1, and it has a width of pi over 2, which means that the actual area, now I'm just going to redraw these again, the actual area is less than that rectangle that I drew, which means that the integral from 0 to pi over 2 of sine x dx has to be less than the height of the rectangle, which is 1, times its width, which is pi over 2. Let's try one more here. So we're going to use, it says comparison properties. So what we have here is e to the negative x squared. Now I know if I plug in a 0 to this, I get 1. And if I plug in 1, I get e to the negative 1, which is somewhere down here. So we've got this curve that goes down like this. And up here I'm at 1 because I plugged in 0. And down here I'm at e to the negative 1, or 1 over e. That means that the integral from 0 to 1 of e to the negative x squared, and I'm only doing this thing from 0 to 1, it's got to be bigger than this rectangle, and it's got to be less than this big red rectangle. All right, so let's do the big red rectangle first. That's simply 1 high and 1 wide, so that's 1. And the green rectangle was 1 over e high and 1 wide. So now we know the answer is somewhere between 1 over e and 1. All right, you should be set for homework number 6 now.